to, first of all, thank everyone for adapting to the weather situation. I mean, considering the weather issues the last day or so, we did a remarkably good job of maintaining the schedule as smoothly as possible. And I want to thank you all for that. It's my pleasure to introduce the first of our algebra candidates, Dr. Kwang-ho Choi, originally from Korea, received his PhD in August 2012 from Purdue. His advisor is Freidun Shahidi. He's held visiting positions at Oklahoma State as a visiting assistant professor and has been a postdoctoral fellow at ICERM in Brown. Has also had visiting positions in Europe, including the Max Planck Institute in Germany. And so we're pleased to have him visit our campus. He'll be speaking today on invariants of L parameters between P-adic interphones. Dr. Choi. Okay.
Okay, thank you so much. Well, I would like to say first that thank you so much for this great opportunity. I am so happy to be here to talk about my research and my current work. Take off, thank you. So, well, in a sentence, my research is about the study on the relationship between two different areas. Okay, in a picture, if we have two areas, for example, and then relatively speaking, the left-hand side is the well-known, and then the objects on the left-hand side are relatively easy to handle. On the other hand, the right-hand side, this is not that relatively known, and then objects are not that easy to handle, so I say the hard to handle. One of the ways to study this right-hand side unknown area is to discover the relationship between the two areas and then transfer the well-developed theory from the left to the right. And then, or if the given question on the right-hand side is complicated and hard to solve, and then we can make it much simpler by turning it into the left-hand side using this object easy to handle. Okay. For example, you can put the group here, group areas, and then you can put the field, for example. Okay? And like this way, the discovery of the relationship between two areas gives us a new approach, okay, to study these unknown areas. Right? In this research direction, I'm going to revisit today the first Galois theory, and then introduce the Langlands correspondence for P-adic groups, and then last, I'm going to talk about my current research. Okay, titled the Invariance of L parameters between P-adic intervals. All right. Okay. So the Galois theory. Okay. This is one of good starts to understand this research direction. Let me give you the fundamental theorem in the Galois theory first, simply. And then the theorem, which was discovered by Galois, like 1823. Okay? And then for simplicity, I'm going to talk about only this field, the field of rational numbers. And then if you pick polynomial inside here, whose coefficients are all the rational numbers. And then I want to note this the Q or the joint F. Okay, this is the field generated by the rational number and all zeros in this polynomial in the complex number, which called the splitting field. Okay. And then also I want to note the G as the Galois group of this splitting field over the this rational number, by definition, then collection of all homomorphisms on this splitting field, and then such that how restricted to this rational number is identical. Okay, good. This is the Galois group, turns out to be finite group. And then the fundamental theorem in the Galois theory says there is one-to-one correspondence between the two different areas here, two different areas. And then the left side, this is the collection of all subgroups. Okay, I want to denote the H of this Galois group G. And then right hand side, this is the collection of all intermediate field, the subfield so-called. Okay, and then I will denote E between Q and the splitting field. Okay, and then as you see, this is a group area and this is the field area, right? And then the fundamental theorem, the Galois theorem says there is one-to-one correspondence. Moreover, this one-to-one correspondence preserves the following maps. So if you pick the subgroup here, this maps to the subfield fixed by this subgroup. And if you pick the one element E under here, okay, so subfield here, and then this maps to the Galois group of this splitting field over the E instead of Q. Okay, the this turns out to be subgroup on the left hand side. Alright? So this one-to-one correspondence gives us the relationship between the two different areas. And then this has a lot of interesting applications. Among them, I want to single out the following thing. Okay, start with the question here. But I better use the other side here. I can start with this question, okay, to see the one of the applications of this fundamental theorem of Galois theory here. The f of x, okay, denoted by the a sub n, x to the n, plus the a sub n minus 1, x to the n minus 1, and then the a1x plus a0 that sits inside this polynomial here. And then the question says when this f of x has a general solution. A general solution, which means all zeros of this polynomial must be obtained by only in terms of addition and subtraction, multiplication, division, and radicals. Okay, only these operations, and then you must have all zeros of this one, and then the question is like this. Okay, for example, the quadratic form. Okay, very general, the usual or popular example of this general solution. So this question quite complicated to solve on the right hand side. Actually, this is on the field area on the right hand side. And then I'm going to make this question much simpler by turning it into the group area. Okay, and which is this is yes. Okay, the question yes if and only if the Galois group of this splitting field is solvable. So solvable is as a groups, okay, which means that if G is solvable, and then there exists a sequence of normal subgroups until the trivial set, and then trivial subgroup, and each quotients are all abelian. Roughly speaking, how to understand that this equivalent relation is just taking one of this operation is exactly corresponding to this one of this the abelian quotient, taking lift, okay, taking lift from the lower to the upper, and then abelian. So that is exactly corresponding to each other. And then this gives us the following conclusion. Okay, this equivalent relation gives us the following conclusion, which is the degree of f, which is n here, right? And this is n bigger than or equal to 5, then there exists no such general solution. Okay, So which says this is Ruffini and Ruffini and Abel's the impossibility theorem. Okay, so well, this theorem was quite complicated to prove at first. Actually, the first proof by the named Italian mathematician Ruffini around the late 18th centuries, and then his paper required 500 pages. So, but as you see, using this equivalent relation, and then I'm going to give you the two further arguments, and then that proves this theorem. Look at that. Okay, we might be able to simplify his 500-page long proof as follows. First one, so the S sub n, this is a symmetric group. Okay, so the permutation group over n letters, and then this is solvable, and then if and only if n is less than or equal to 4. And again, still this is a group theory. And second argument we need is for any n, so there you can generate polynomial inside here, okay, such that the degree f is n as well as the Galois group of this is isomorphic to S sub n. So any n, it is possible. There is the algorithm how to generate this kind of polynomial. Okay, so as you said, we need just this equivalent relation, and then which gives us some transferring the given complicated equation to the simple equation on the other side, and then using this kind of object, which are relatively easy to handle, and then we prove this theorem. Okay, so this is a good example. Also one of the good applications in the Galois theory. So that's all about the Galois theory that I want to talk about today. And then let's move on to the local Langlands correspondence for P-adic groups. This is another study in that research direction that I discussed earlier. So the study relationship between two different areas, and then transferring the developed theory from one side to the other side. And also, furthermore, this is quite crucial to explain my research interest later. Okay, so let's talk about this one. But before I get in details, I need some background. Okay, there is the field of P-adic numbers. Okay, I would like to note that this is the Q sub P, and then the P is just any arbitrary prime number. Okay, as a set, this the field defined by the Hensel around early the 19th century, and then as a set of just the collection of infinities here. Look at that, and then so n is from the negative k to the infinity, and the a sub n to the n. This a n is between 0 to p less than p, and you can take a k as any integer here. So as you said, this is infinite sum, and then by taking the a sub n to be 0 from certain point on, and then you got the finite sum, and then such a finite sum contains all the rational numbers. So that means that this Q sub p contains the rational number. Even more, we can obtain the Q sub p by taking, I have to write it the other way, by taking topological completion. In order to take a topological completion, we need a metric that is with respect to the hierarchy like this one. Okay? So we call this is a metric, and then we call it the P-adic metric. Okay? And the OR P-adic norm. All right? Let's take a moment. Okay, let's take a moment to understand the P-adic norm. All right? So if you take just the 12 inside the Q, okay, And then since 12 is the 2 squared times 3, so if you take the 2 adding norm of 12, that is 1 over 2 squared, which is 1 over 4. And then if you take the 3 adding norm of 12, that is, since 3 is only one has one power, and then that is 1 over 3. And if you take maybe the 5 adding norm of 12, there is no 5 there, so you got the 1 over 5 0 equals to 1. So something like that, right? So you got some graph, some the understanding, okay, concept of the P-adic norm, right? So with respect to the P-adic norm, P-adic metric, you can make a topological completion and then you obtain this field, P-adic numbers, okay? So another way to understand this field is instead of this metric, you might be able to take a topological completion with respect to the usual effect value. So I want to denote like this one, usual effect value, and then you obtain the real number. Right? So the real number, and then which is much familiar to us than the other one, but somehow this is just by taking different matrices and then taking same topological completion, and then we got these two different fields. So I believe we have a small concept about this P-adic numbers. Okay, and so I want to talk about two more things about this P-adic number. The first one, since you took the topological completion from the Q with respect to this kind of special matrix, different from the usual absolute norm, absolute value, and then the first one, QP has the locally compact topology. Also, the totally disconnected. There is this kind of property is exactly coming from, especially the totally disconnected coming from the property of the P-adic matrix. Okay, so this is the first property that I want to tell you. And the second one, this is quite the deep theory, and then also quite a difficult object which is newly established from this field of the P-adic number. Field of the P-adic number. I want to give the name first. This is the Veil group. This is a newly generated topological group, okay, which is induced from this QP, Q sub P, okay, and also this Veil is coming from the French mathematician Andre Veil. Okay, so the Veil group. I want to know that this is WQP, okay. And then this is a locally compact topological group. Also, this has a dense image inside the absolute Galois group. Absolute Galois group means the algebraic closure of QP over QP. Okay? So, and moreover, the WQP sits in the following exact sequence. That is as follows. So, this absolute Galois group, and then you can take the Galois group of K bar over K. Okay? And then here's a K is the residual class field of the Q sub P, the isomorphic to G bar P field of P order. Okay? Here. So this guy is acting on here, but you can collect the certain subgroup actually trivially on the here. And then there is, we call it inertia group. I'm going to go here, IP. And then the absolute Galois group sits in this exact sequence. But since this is a dense image, and then you generate the new exact sequence like this way. So you can take IP is the same here, and then something here, and then you take actually this is bigger than the set of the integers, which is Z, and then you only take the Z as a subset here, and then you generate, this is you generate a new group here, that is exactly the very group here. So this is a W, and then there's image here. So, yeah, go ahead.
What's the closure K mean here? Define.
Yes, this is a residual class field. If you have the Q P, and then you got the ring of integers inside this field, and then the ring of integer is local, so they have a unique maximal idea up to the unit. So you can take a maximalize and then take mod out, and then there is it turns out that there is a field, finite field. So that is related to this. This P is very related to this P.
Oh, okay, yeah.
Okay. Yeah. Other questions? Yeah.
The absolute Galois group of the P-adics, is that still profinite and is it still locally compact?
That's true. Yes. Moreover, this is
Both
a
of them?
compact.
Compact.
Compact. This is a compact.
Okay,
So
so
that's-
what about profinite?
Yeah, profinite. So the profinite is exactly what you said. This is just some the inverse taking the inverse limit of finite groups, and then you got the here. So there is the property of the inverse limit gives us the compact topology. So that this is compact. Yeah. Actually, quite a good question actually, because this is compact. So somehow the following theorem, what I'm going to tell you, there is a somehow you generate we started the 2P field, and then we got some group somehow related to Galois. So there is a relation between this group stuff and then field stuff, Q sub P. But the people try to understand something in the Galois side corresponding to this field, but this is locally compact. This is compact. So there is some little difficulty in finding certain locally compact group. So that is related to that one. Okay, so let me make it precise here, okay? Actually, here there's a local class field theory approved in 1930 by the Paste or the Artin, and then the Tate, and the many mathematicians, and also the many different types of proofs, and then which says the WQP, we take the Abelianization, which means the WQP, since this is not Abelian, how can you make the Abelian group from here, take mod out, which is commutator subgroup. And as for the topological region, you can take the topological closure. This is the group side, all right? And then we got the Q sub QP, this is a field, and then take the multiplicative element, turns out to be Abelian group. So there is isomorphism here, okay? So moreover, this is topological structure preserved. This is locally compact. Since that is locally compact, this is locally compact because this is locally compact. So this is a topological. Okay, but this is Abelian. So both are Abelian. As we see here, this is Abelian. So actually, there is a very deep theory. Actually, yeah. So
How big is that absolute Galois group?
I'm sorry.
How big is that absolute Galois group?
Yes, if you replace the Abelianization of absolute Galois group, this is no longer isomorphic.
Right.
Yeah.
The absolute Galois group of the P-adics, what's its cardinality? I'm still thinking back in the previous
Is it
frame.
AB here?
No. The absolute Galois group of the P-adics.
Absolute Galois group of P, this
Yes,
one.
yes. I'm
Yeah.
still thinking back there. How big is it? Is that still continuum?
Actually, I'm not sure that you are familiar with these guys. So
Okay,
this
yeah.
is the collection of all topological completion and running through all P's. We fix the P only, but this is taking all P's, so huge. But this contains Z. So just the difference between this big group and smaller group, that is exactly the difference here. So how you realize how big this is exactly the same amount of how big this is.
Okay.
Then here. Okay. Other questions? All right. Good. Okay. So in that sense, the local classification theory can be understood as an extension of the Galois theory. There was just one-to-one correspondence, but this is as a topological group. Right? And now it's time to talk about the local Langlands correspondence. Right? So let's do the special case first. That is about the GL and QP. This is the collection of invertible matrices and whose entries are all the QP. Okay? This is special case, and then I'm gonna give these two spaces, right? And then the left hand side, I'm gonna write down the one by one. That is, the left hand side is the collection of the equivalent relation of the irreducible, the smooth, okay, homomorphism from the given group GL and QP to the group of automorphism of complex vector space. Okay, and then usually the V is the complex vector space of one-dimensional or very often the infinite dimensional. Okay, and then I didn't tell you about the definition of this, but instead of giving full definition, let me give you the brief idea of what is irreducible and what is smooth. So first of all, smooth is you can understand this homomorphism as a continuous homomorphism. So we have topology and the other topology, so you can understand the smooth homomorphism as a continuous homomorphism at this moment. Irreducible means that this homomorphism, when we say the irreducible, and that this homomorphism does not factor through the automorphism of W. W is a proper vector space of V. So if that doesn't happen, and then we say that this homomorphism is irreducible. Okay, so we have some rough idea of this. I think at this moment there is error. Okay, so actually the name of this homomorphism is the reducible. Actually, the representation. In this sense, I wanna denote this set to be RDP over GRN. Also, I wanna give the name of this homomorphism. That is a pi. Okay, pi from this domain to this target. Okay, and also the one example in the lab here. So the REPGLN, and then what can be the typical example inside these huge spaces. Take a GLN here. You can take a determinant. This maps to here, and then we know the isomorphism here, right? Here, so that you got the. Oh, I'm sorry, not the isomorphism. Actually, we know the P-adic norm. This maps to the C star, okay? And then you understand that this is exactly the automorphism of the C. Just that you take C as one-dimensional vector space, okay? So this is one of the typical elements inside the REPGLN, okay? So I want to know this is a DEP and P. Okay? So this is on the left-hand side. Okay, we call it the representation side. Right? And then the right-hand side, that is the set of equivalent classes of the continuous homomorphism. So from now, it's time to use the variable. That is W, 2P, and the SL, 2C. Okay, to the certain complex the V algebra corresponding to this guy. There is the GL and the C. Okay, so I want to know this is P. Okay, and then with some certain conditions. Okay, so and also I want to denote that this is as just the P of GLN. Like this way, okay, like this way, I want to give the one typical example inside here. So there is a P and GLN, and then what can be inside here? You can take the W, the Q sub P, okay, and then you can take this quotient, right? This take a mod out this commutator subgroup. There is W, Q sub P abelian. And then we know that this isomorphism, right? This is the local classic field theory. This maps to QP star. I want to note that this is ART. Okay? And then this is quite similar, right? And then take the P-adic norm. This maps to C star. And then C star can be embedding into GL and the C. You see here. We start with here, and then we end up in with this one, and then we get to that guys. I want to denote that this is as ART. And this is one of the typical examples on the right hand side. As you said, I didn't use SL2C, right? But this doesn't work too much at this moment, right? So, for example, the real group case, instead of the P-adic group, we do not take this on the right hand side. So, no worries about this term at this moment, okay? So that's why I didn't use it here. Okay? So, I introduced the left hand side, and then I use the right hand side, and then And then I gave the 2 examples, and then so also the name of this P, like this pi was called the representation, and this P called the L parameter. Somehow L parameter is some certain continuous homomorphism from here to here. Okay. Okay. So there's a couple of remarks that I want to make here. So the first one, as you see the left-hand side, we very often take care of this infinite dimensional vector space V. Infinite dimensional vector space. As you see here, what about the GLNC? That is just a finite vector space bounded by the number n. So the right-hand side is somehow, the legal easy to handle in this sense. Okay. And the another one is by taking the n equal to 1, and then what about the GLNQP, GL1QP, turns out GL1QP, this is nothing but just a QP star. Actually, this is coming from local class field theory. Okay, so which is abelian case. But if you take n is bigger than 1, GLN is no longer abelian. Okay, this is not abelian. So in that sense, you can understand that this local Langlands correspondence for GLN as an extension of local class field theory from abelian case to the non-abelian case by taking the n is bigger and bigger. Okay?
So which slide you said it's easier?
I'm sorry? Oh, yes, yes.
Slides. So you said one is easier.
Very good
Which
question.
one?
Very good question. Actually, I also thought about that way. So, but many people, many people usually put the representation on the left-hand side and then put the L parameter on the right-hand side. So somehow like that way. Yeah. So, and then here's the theorem. What is the local Langlands correspondence of GLN? This is now theorem proved by the Harris and then Taylor and then the Heniat and then the Wistry Short. The Harris and Taylor proved this theorem in 2001, and independently Heniat proved 2001 again. And then this conjecture, the theorem was actually the main part of number theory and representation theory, and then Short, he proved 2014 again, polarity difference method. So they're still very continuously interesting object. So which says there exists one-to-one correspondence between this representation side and then L parameter side. Okay, and also satisfying the certain nice property. So one of these properties is preserving L function. The L function is the uniquely, if it is possible, uniquely defined by the given representation, also given L parameter. So independently they define each side, but they are matching each other through this one-to-one correspondence. Okay, and also the example is through this one-to-one correspondence, these two guys matching each other. Okay, the example that I gave you.
If I were going to try to make a category out of forms, would the morphisms be what I think they are? Would they just be things that make the right diagram commute?
Yes.
Okay.
That is a quite a good question. Actually, that gives us the how to expand this kind of special case to the general case.
Right.
Yes, that's quite a good question. Are there any other questions? This one is okay.
Is this going to be some kind of categorical equivalence?
Yes.
Okay.
All right, and this is the local Langlands correspondence for GLN. And here, now it's time to talk about the general notion of local Langlands correspondence for the general setting. Okay. So in order to cover this, guys, I need to bring in the new terms. That is the connected reductive algebraic group over QP. Instead of understanding these whole things at this moment, you can just take these groups as matrix groups. of course, one of them, the GLN, I covered here, and also maybe SLN or the SP2N, and so on. A lot of examples here, but not always very true. But at this moment, you can take this one as a matrix groups. Okay, this is true. I want to do this is G. Okay, and then again I want to write that this is REP of G, and this is parameter side of G. Okay, and then if you take the element here, that was actually the starting GLN QP, as you may remember. This is a start with the G to the automorphism of the here, the infinite dimensional complex vector space. I changed the G here from the GLN. Okay, but this was changing here. So another one here, the other one here. If you take the element here, L parameter, the domain is the same. Whenever you change this group from the GLN to the general case, the domain is the same, but target is different. So since I changed here from the GLN, this was GLNC, but now this is different. So I want to write the G hat, okay? And then maybe you have to write the WQP here. But like the SL2, you don't worry about this too much at this moment. Just understand this one from the WQP to the G hat. What is G hat? That is exactly complex Lie group, like the GLNC. Okay, GLNC like this one, and then this is uniquely determined by this given group G. For example, if you take the SLN, actually the GLN case, this was the GLNC. If you take the SLN, and then this is a PSLNC, okay? Something like that. So given this one, that is changed, okay? And also, as before, the V is a very often infinite dimensional, but you see here that this is actually the complex Lie group, which means actually the over finite dimension. Okay, so you got the infinite dimension on the left, and you got the finite dimension on the right. Okay, the conjecture, actually this is not theorem yet, unlike the GLN. So the conjecture says as follows. Okay, conjecture, this is a local Langlands correspondence conjecture, and then this is established by the Langlands. His letter in the 1967 to the Andre Weil. I mentioned the Andre Weil. So the Weil group, right? Weil group is after the Andre Weil. So he wrote a letter to him and then about this conjecture. So this conjecture sits in his letter. So which says, instead of, you may remember the GLN case, that was one-tone correspondence, right? GLN case one-tone correspondence, but now instead of one-tone correspondence, there exists subjective with finite fiber from this left side to this parameter side. Okay? Good. So subjective finite fiber, and then also maybe the satisfying the couple of nice properties. So because this has a finite fiber and the subjective, if you pick the L parameter and then consider its fiber in here, okay, pre-image should be finite. Subset here, and then I want to denote this is P of G, okay, and then we call it, this is the L packet. L parameter gives us L packet, which is finite. Okay, one of the properties in this local Langlands correspondence as a conjecture is you can parameterize this finite set in terms of the certain stuff in the L parameter side. So this can be on the left hand side, but parameterized using the right hand side object. Okay, all right.
Does there have to be some kind of a bound?
I'm sorry.
The finite sets. You said how to calculate them, but can they be of unbounded size?
Yes, this is bounded for special case. For example, the SLN case, that the number which bounds this guy is very related to the size of this guy. That's just I wanna. This is QP, right? QP. Because in general we don't know. We don't know. In general, group G, we don't know how to bound these guys. All right, and then, so I want to talk about the two things about this conjecture. This is a finite, actually the set, right? So this is very huge space. The given parameter, and then you consider the pre-image L packet, and then instead of studying this whole space, huge space, you can partition into finite set. Each finite set holds L packet and indexed by this parameter. So this local Langlands conjecture gives us a new way to study these huge spaces, as just boil down from the infinite space to the finite set. And another one is some example that I want to tell you. That is how powerful this local Langlands conjecture is. Okay? So you consider D, okay, as a quaternion division algebra that is over 2p, d4. This is no longer period. Okay? As I said, you can define this is x0 plus x1 I, x2k, and then x3k, and then this all xi is inside qp. But a certain relation. Because of this relation, this D is not abelian as multiplication. So this is a division algebra, the quaternion division algebra. The collection of multiplicative element here, I want to do this now. This is one of the example of connected deductive algebraic group. Okay? And also we can consider it's a subgroup. This is the it's a commutator subgroup. Also, this is one of the example of the connected deductive algebraic group. So people can study the representation of this bigger group and then take a representation. Then numerical object is quite interesting to me, and then the people try to count how many sigma is inside the distribution. So that is the multiplicity of sigma, how many times this sigma is repeated inside pi. So this is quite difficult to understand only on the representation side. But however, using the local Langlands correspondence, this is exactly the same amount of the dimension of irreducible representation of the only following four cases. That is trivial case, where the G mod 2, abelian, and the Klein 4 group, and the Quaternion group, the order 8, finite, non-abelian group. So this was quite difficult to understand, but now we can translate it on the L parameter side, and then so it turns out to be this is either actually 1 or 2, just using the small amount of representation theory of a finite group. So this is exactly either 1 or 2 using the local Langlands conjecture. So you see how I made this difficult, actually complicated question, the simpler question, right? So.
But it's a conjecture.
I'm sorry.
It's a conjecture.
Yes, very
You
good
don't
point.
know.
Actually, this is about in order to get this guy is we need the local correspondence for the SL2 and then D1 and then the D star and then GL2. So actually, fortunately, these all four cases are known. So
Okay.
yeah, very good question. Actually, you pointed out the part where we know.
So is this something you studied in your research, or is
there is a norm. Like my research generated this case to the general N. So this was only the 2x2 cases, 2x2 use case. But this is known before my year. Yeah. So this. Well, the local Langlands conjecture is also one of my research interests. Recently, in my joint project with Wittek and we proved the local Langlands conjecture for the inner form of SP4 case. This is a joint work with Wittek. And then the other one is the recently we started work the local Langlands correspondence for the following cases. This is the G-spin 4 and then G-spin 6 and then all the inner forms. This is a joint work in progress with the Mahdi Asghari. Okay. So, what we've done so far is we start with the Galois theory. That was 1923. It was just one-to-one. Extended it to the local stress field theory. That was 1930. Okay. Not only one-to-one, but also isomorphism preserving group structure as well as topological structure. Okay, but the Avelia extended to the local Langlands correspondence for GL and QP, right? And then this was 2001 and then 2014, and then this is a one-to-one correspondence but covers non-abelian case. This is actually some part of local Langlands conjecture for general case. That was the subjective with the finite domain. Okay, so we are here, all right? We are here, so that you see how we extend, okay, the previous result, and then get the new, okay, concept. All right. How many minutes do I have?
Maybe another 5 or so?
Yeah, around
Yes.
5 or so.
Okay,
Good.
good. Uh-huh.
Okay. So, the rest of my talk, I'm going to talk about my recent work, and then since it's only for 5 minutes left, and then I'm gonna do with less technicalities. Okay, so instead I'm gonna give you the brief concept and then the more inspiring. Okay, so that one is here my current research. All right. So I have to introduce the P-adic inner form. Instead of giving you the full definition of these guys, let us understand quickly with the following example. Okay, so there is the G and the G prime. So actually the G is given. Actually, I wanna again use the connected, the reductive algebraic group over QP as understood as just the matrix groups. Okay, and then I wanna add the quasi-split. But instead of giving the definition of quasi-split, and then these following examples are quasi-split. So you can take the simple, the GL2QP, or the SL2QP. So why we call it quasi-split? Just roughly speaking, this kind of matrix contains the special subgroup consisting of upper triangular matrix. Of course, this guy has upper triangular matrix, so we call it quasi-split. All right? Instead of G prime. Okay, G prime, actually this is the same, the connected algebraic group over QP, but I want to call it non-quasi-split. Since it doesn't contain the upper triangular matrix, but I want to call it this is the inner form over G. So because this inner means G and G prime, they are connected by inner homomorphism on the level of QP bar, the algebraic closure level. So what kind of inner forms they are here corresponding to each example? There is a GL2 case. What about the inner form of GL2? There is a D star. I already gave you the D star. Sorry, I erased that. So D star is the collection of a multiplicative element in the quaternion division value. And then what about inner form S2? There is a D1. Okay, it's a commutator sum. So for these guys, you can use this example and understand the inner form. So this is a quasi-split. This is an inner form over G, but non-quasi-split. Okay, so like this way. And then more importantly, why I brought the inner form, that is because they are connected by inner automorphism, and then you remember this head group, actually so-called L group, that is used instead of GLNC, right? GLNC. So this is the same. Okay. And the second one, because this is the same, okay, you remember the L parameter start with like this one maps to some G hat. Since this is the same, so you might consider certain relation between this the set of L parameters of G and G prime, right? Because the targets are the same, mostly same. But because this different structure, one is quasi-split, the other is non-quasi-split, although they have the same this head group, and then this is a proper subgroup. Okay? So because this is the inclusion, we got the following nice research topic. Look at that. This is actually my the main some current research interest. That is the again I want to use these two circles, different areas. And the left hand side is representation of quasi-split, like that. Right hand side is non-quasi-split, but they are related by inner forms. Okay? And then, but this is since it contains some Borel subgroup I mentioned before, the upper triangle matrix. And this is quasi-split, and the left hand side is quite well known. Also, the objects are easy to handle. For example, Whittaker model is here. Unfortunately, since this is non-quasi-split, G prime, this is not that well known. Also, the objects in here are relatively not that easy. So, my main goal is to understand this area. My main goal is to understand this area. And then, as we discussed so far, the one of the ways to study these guys is understand the relation between these two, and then some certain known factor from the left to the right. But these two spaces are very, very huge. But we know the local Langlands conjecture. Local Langlands conjecture says, let's apply local Langlands conjecture to here. Okay? There is what? There is a projection map from here to the L packet, the L parameter of the quasi-split. Again, local Langlands correspondence said we have another surjective with a finite map here. But since there is a subset inclusion, you pick one element here, and then you got the finite L packet on the non-quasi-split, right? This is exactly pre-image of the discrete. Since this inclusion, that can be understood as L parameter here, so this gives us the other L packet, which are finite. You remember that, right? These two guys are finite. Instead of studying the relationship between these two huge spaces, it is enough to understand the relation between two finite steps. So we just reduce this huge study to the finite cases. Okay. So with this in mind, the following question makes sense. Okay. That is exactly. Okay, just pick element in the L packet of quasi-split, pick the other element from the non-quasi-split, and then question says some representation object attached to pi, and then the representation object attached to this pi prime. So question is exactly like this way, but this representation object is this OBJ, then means some several representation theoretic object, but one of them, and I want to single out this representation object equal to R group. So and now the question goes to exactly R group of pi, and then R group of pi prime. There is some relation here. Okay? This is part of the joint work with David Goldberg. So this R group is a representation theoretic object, and then this is a finite group. So you start with the infinite dimensional representation. So you obtained a finite group attached to this pi and pi prime. So studying this R group, you got some certain information, okay, which is coming from this infinite dimension. So there is one of objectives why we need to study the R group. Okay, so and then we answered this question. Okay, for the following special case recently, theorem 2014, the joint work with David Goldberg. Especially, G is the following groups: the SP2n, SO2n plus 1, SO2n, and the SO2n star here. Okay. In this special case, we call it the classical group case. The R group pi is same with R group type prime. The quite good. Yeah. And then so well I mentioned before this is the quasi-split size is well developed. So the Goldberg proved that this is the isomorphic to this quasi-split size isomorphic to the G mod 2G to the certain power. But until this theorem, we didn't know the structure of these guys. Okay, very few cases of this guy, but the whole cases we now prove this is isomorphic to here. This is one of the application of this theorem. Also the other application, I want to finish by giving this brief to the other application. That is, many people study the representation of this bigger group, G prime, and then using the representation of the smaller group. We call it the reducible, and then pick the sigma, taking the induction here. The problem is the induction is newly defined the representation on the upper level. We don't know when this is irreducible or not. So determination of this irreducibility of inducible representation is quite an important object. So for example, the applying to the trace formula and then also the automorphic forms and then representation there. So this is quite a serious object. So I write the prime here. Okay? But until this theorem, we didn't know what's going on when this is irreducible or not. But I mentioned before the left-hand side, this is non-quasi-split side, right? I'm using the prime, right? The left-hand side is also same. So you can get the here, and then you got the here, and then take the sigma, and then take the induction of the sigma. This is sigma prime, and this is sigma. It's the same thing, but this is the quasi-split side. This is well studied, okay, by many the mathematicians. So we know quite good. Okay, result. We have quite a good result in here. So until that theorem, we didn't know how to handle the reducibility of this guy. But now one of the application of this theorem, the induced representation sigma is irreducible if and only if induced representation sigma prime is used. So this is the other application of the theorem that I want to talk about today. Let me start here.
Any questions?
Did you get any strange behavior, some difference between representations of G and G prime?
G and G prime.
Did you notice something strange, or everything matches like here?
Yes, actually very good question. Actually, one of the good example that I show you, that is a G and G prime. Actually, this is a D star in front. This is a GL2, and then this is a D star. And then I gave you how to take care of the multiplicity of the representation from the D star bigger group to the smaller group. That is a 1 or 2. I showed that as an application, but you can do the same thing on the left-hand side here. The SL2. We can count the multiplicity of representation GL2 in the restriction to the SL2. Unlike the uniform side, but this is always 1. So that is one of the phenomenal actually.
Okay, so when you restrict from D cross to D1, it's always multiplicity 1. Is that what you are saying?
Oh, no. I'm saying that
this
this
side.
one. Yes, this is always multiplicity 1, and then but this is either 1 or 2. I mentioned that earlier. So that is the different phenomenon, which is arising only on the non-quasi-split uniform side. So the different phenomena, so you can distinguish.
Any other questions?
And then you have in one pocket on G prime side,
Okay.
R groups for all elements in the pocket are same. Is this what you'll get?
Especially this case, your argument is true,
Mm-hmm.
but we don't know yet.
Okay, so did you?
Yes, I expect it, yeah.
How did you prove it, or is that what did you use to prove that you have same R group for all elements in the pocket on
Uh,
G prime side?
Yes, just that is one of the consequences of this one. So this pi is just the arbitrary
Mhm.
element. Pi prime is also arbitrary element. So the this is the isomorphism gives us the just pick one pi, and then I want to denote to pi 0, and then you just change pi prime. That's I want to denote pi 1, also the pi 2. But this theorem says this is isomorphic this one as well as this is isomorphic this one. But pi prime 1 and pi prime 2 are
But you're
coming from
using
the
parameters,
Yes.
right? How do you get parameters on G prime side, on the inner form side? How do you get parameters?
parameters. Parameters the same with the this G,
Mm-hmm.
but since the structures are different from the G and G prime.
So do you use Arthur's result for, what is the description of parameters you are using?
I see. Now, so you have the WQP. So this gives us the parameter of the G, right? And then this is the same. So this is the same, can be understood the same parameter of G prime. But I start the parameter of the G prime.
Okay, no, but I'm asking,
Is it-
you have pi,
Uh-huh.
and you attach this parameter, so you
Oh, no. Actually, I'm sorry. Actually, I think that this following answer will be make your question clear. The P inside is fixed, actually given.
Mm-hmm.
And then I choose pi later.
Okay, so how do you know this? So that's what I'm asking. Is this from Arthur's result?
Yes, that's true. Yes, I'm using the this is R. Yes.
For both sides?
Yes, for both sides.
For both
Yeah,
sides.
for both sides. Yeah, right. In this sense, right, that I have to make a clear this theorem. After the result for this quasi-split case, there is a proof completely for now. But the inner form side, G prime side, he just stated the arguments with the pure proofs. So in that part, this theorem assuming the other part of the Arthur's result. So this theorem contains the mild conjecture, the CDT.
So it is just he announced, right, but didn't prove.
Yes,
or
that's true.
Any other questions? All right, let's thank our speaker again. You're all, of course, welcome to join us upstairs for the reception.